going to prove the first principle of mathematical induction using the well-ordering principle. So remember the well-ordering principle. Every non-empty set of positive integers contains a least element, right? So if this set is a subset, if this set S is a subset of the positive integers, and this set is not empty, then there exists an element A, where A is smaller than all the other elements in B, right? So we're going to use this in order to prove the first principle of mathematical induction, which states that if S is a subset of the positive integers, we suppose that 1 is an element of S, and whenever K is an element of S, it follows that K plus 1 is also an element of S. Then S must equal the positive integers, right? And this is the equivalency of this statement. We're going to use these to do induction in general, but I'm going to do the proof of the first principle of mathematical induction using this right here. Okay, so let's go ahead and get started. So we can rewrite this statement of the first principle of mathematical induction. Okay, let me scoot it a little bit. So we have S is a subset of the positive integers, right? S is a subset of the positive integers, and, or I guess where 1 is an element of S, okay? 1 is an element of S, and we have, and if we have, let's put it like this, if K is an element of S, this implies that K plus 1 is an element of S, right? So this is our P, right, statement, because this is a P implies Q statement, right? Because if we have S where it's a subset of positive integers, then this, right? So our Q is going to be S is equal to the set of positive integers, right? Okay. Well, we're going to do this by contradiction. So we're going to want to do proof by contradiction in the form P implies Q. So remember from basic logic, if we know that the negation of P implies Q is logically equivalent to P and not Q. So for a proof by contradiction, we're going to assume P, we're going to assume our whole hypothesis and the negation of our conclusion, and we're going to show that this statement is false, meaning the negation of our whole statement, right? The first principle of mathematical induction, right? Our whole statement, the negation of that is false, meaning the first principle of mathematical induction must be true. Okay, so let's go ahead and do a proof by contradiction. Okay, so we're going to suppose P and not Q, right? We're going to assume S is a subset of the positive integers, where 1 is an element of S, and if K is an element of S, then K plus 1 is an element of S. And we're going to assume the negation of Q, which we're basically going to say S is not the set of positive integers, right? Okay, so if S is not the set of positive integers, then thus there must exist a set T that is a subset of the positive integers, right? Where S union T is equal to the positive integers, right? Because if S is a subset of the positive integers, and we're also assuming that S is not the set of positive integers, then there must exist another subset of the positive integers, right? Where the union of S and that set must be the positive integers. Okay. Another thing is T intersection S is equal to the empty set. So these are completely separated. And of course, T is not empty. So, right, there's going to be the subset T that is a subset of the positive integers, where the union of S and T is the positive integers. Their intersection is empty, and T is not empty, right? Oh, I guess I should put empty. Okay, so since T is a subset of the positive integers and T is not empty, we can use the well-ordering principle, right? So by the well-ordering principle, there exists an A contained in T that is the least element of T. Okay, so if A is the least element of T, and T is of course a subset of the positive integers, right? And 1 is an element of S, that must mean, right, that this must mean that A must be bigger than 1, right? Because if A is an element of T, which is a subset of the positive integers, and 1 is an element of S, right? Well, 1 is the smallest positive integer, right? So that means A must be another positive integer bigger than 1, right? Okay? Okay, and this implies that 0 is less than A minus 1, right? Which of course is less than A, right? Since A is the least element in T, that means A minus 1 can't be in T, right? So this means A minus 1 is not an element of T. And of course, if it's not an element of T, where else could it possibly be? It must be in S, right? So this means that A minus 1 must be in S. Well, if A minus 1 is in S, right? Remember, we assume that if an element is in S, then that element plus 1 is in S, right? So this means A minus 1 plus 1 is an element of S. And of course, A minus 1 plus 1 is A is an element of S. Well, this is a problem because we have that A is in T and A is in S, right? But we assumed that T intersection S was empty. But if T, right, has A in it and S has A in it, this means that S intersection T is not empty. So you can have their intersection be empty and their intersection be non-empty, right? So this is our contradiction. Okay, so as you can see, assuming S is a subset of the positive integers where 1 is an S, and if K is an S, then K plus 1 is an S, and assuming that S is not the set of positive integers leads to a contradiction. So that means P and not Q must be false, which means the negation of P implies Q is false, which means P implies Q must be true. So thus, the negation of P implies Q is false. And of course, therefore, P implies Q is true. Essentially saying that the first principle of mathematical induction must be true.